All right. It says here that iron was reacted with the solution. So here's what we've got. We've got elemental iron plus a little copper sulfate. That's going to give us copper plus iron 2 sulfate. Okay. And here's what we got. We got 400 grams of copper 2 sulfate will react. And it wants to know the percent yield or how much copper we're going to get. So here's what's happened, okay? I have taken myself a piece of iron. Yes.
Didn't it say we were going to get 151 grams?
Yep. So we're looking for the theoretical yield, right? And the actual yield is what, John?
151 grams.
Okay, 151 grams. So I would expect this number to be higher or lower? Higher, right? Because if that's what Jethro back there in the lab has scratched around and got actually, I would expect this number to be a little bit higher. Okay, so here's what's happening. What type of reaction is this? Right, single replacement, right? So I got myself a good old piece of iron, and after an hour, what I'm noticing is there's something growing on that iron. And what's growing on it is copper. So see, we're copper plating out a piece of iron. Now that means that this is in excess. Why? Because if there's only one mass given, the other thing is in excess. All right, so here's what we got. We got 400 grams of CuSO4. Now I think copper weighs 64, or is it 63?
63.5.
Okay, so 63.5 plus 32 plus 16 times 4 is 159.5 grams of CuSO4 per 1 mole of CuSO4. All right, let me stop and be sure I'm balanced. 1, 1, sulfate, sulfate, copper, copper. So we're balanced. That's something I forgot to do, which is really risky business, is you have to be sure that you are balanced. We are. Okay, what's my ratio then between copper sulfate and copper? All right, so 1 mole of CuSO4 for 1 mole of copper. Somebody just told me it weighed 63.5 grams of copper per 1 mole of copper. So 63.5 divided by 159.5 times 400 equals 159.2 grams. So remember, this is the theoretical yield. And naturally, it's higher, just as we expected, than the student or the chemist scratching around in lab. All right, so what's the percent yield there? Well, it's going to be the actual yield, which is 151 divided by 159.2 times 100. So that's going to be a 94.8% yield. Who got this?
I got really close to that.
You got really close. Well, good. Yeah.
That little step right there between when you're doing the math, I didn't do it, and I got the same answer. What is that?
Here? All right. This is your stoichiometric ratio. Now, the reason that you got the same answers, look at what we're doing. We're just multiplying by 1. So anything you multiply by is 1. Here's why you got lucky, as that number's a 1 and that number's a 1. Had that number been a 3 right there, then you would have had to have put a 3 right there. Does that make sense? Had that number been a 5, you'd have had to put a 5 right there, and then it would have mattered. All right. Now you got the right answer, but the only reason you did is you were lucky that these numbers were 1. Okay. That's to be expected. It turns out that single replacement reactions work very dreamy. A 95% yield is wonderful. Like in organic chemistry, one of the things that I try to shoot for in a reaction is to keep the yield above 80. So that way you got some student down there scratching around. They're supposed to be making aspirin. If it's above an 80% yield, they can see white crystal flakies in their hand. That's good, right? When you're learning at the community college, right? Okay, number 47 says what? it says that methyl alcohol, right, this is your wood alcohol, is made by reacting carbon monoxide plus a little bit of hydrogen gas to give you the CH3OH, that's your methyl alcohol. And here's what it wants in the presence of a catalyst. How much alcohol can be obtained by reacting 40 grams of CO and 10 grams of hydrogen? And how many grams of excess reactant remain unused? All right, so we are looking for CH3OH. Okay, that's the methyl alcohol there that we are trying to get. Now, we got two masses, so it's not possible to determine which one is limiting. So that means we got to set ourselves up two equations. All right. 40 grams of carbon monoxide. All right, 1 mole of carbon monoxide is going to be in how many grams? Well, 12 plus 16 is what? 28 grams. This is calculation Roman numeral 1. Now, what's my ratio? 1 mole of CO per 1 mole of methyl alcohol. Okay. And in 1 mole of methyl alcohol, that's going to weigh 15 plus 17, 32 grams of methyl alcohol. So when we're done here, I'm going to have an answer of methyl alcohol. Okay, so 32 divided by 28 times 400 is going to be 457.1 grams of methyl alcohol. How much? Times 40, thank you. I typed in 400. So is 45 better? 45.7? All right. Now we're not done yet, right? Because remember, to get this problem, we got to do the second one. 10 grams of hydrogen. 2 grams of hydrogen for each mole of hydrogen. All right, now what's my ratio? It's going to be a 2 to what? 1. 2 moles of H2 per 1 mole of methyl alcohol. Okay. And 1 mole of methyl alcohol, that's going to be 32 grams of methyl alcohol. So 32 divided by 2 divided by another 2 times 10 is going to be 80. All right, let's stop. Somebody said 160. What's happening?
You didn't divide it by 2 the second time.
Yeah, I didn't divide it.
Okay, that's fine. 80. I just want to be sure that I'm not screwing up here, right? So we got 80 grams. So now which one is the smallest number? It would now be this one, which means your limiting reagent is carbon monoxide, right? That's the one that's the smallest. Now we can erase this. See, this no longer has any meaning. This was used as a one-time comparison only because all calculations must originate from the limiting reagent. Does this? No. So that can now be flushed. So the answer to the first part of the question says how much methyl alcohol could be theoretically produced? 45.7 grams. Take note, you cannot add 40 plus 10, right? Because there's still some of this left over. What does limiting reaction mean when we're done? How much is going to be left over? 0. But there's still going to be some of this left over. How much?
I mean, no. 10.
Okay, how will we go about figuring it out? There's a couple of ways. Somebody give me a bright idea.
Figure out how much
What are we
hydrogen's
looking
reacting with.
You want to figure out how much hydrogen's reacting, and how do you want to do that?
Take your 40 grams
Yep.
times moles of carbon
Okay.
dioxide.
Now, I'm going to tell you, I like this better than using that conservation of mass crap. Me personally. You do whatever you want to do. I don't care. You could say, okay, this is weighing 45.7. That's used up completely, so that's 40. So that means 5.7 must be used. So how much is left over? It'd be 10 minus 5.7 to be what? 4.3. Okay. Is that what you want to do? Okay, now here's what she wants to do. She got 40 grams of CO, 28 grams of CO per 1 mole of CO. All right, in 1 mole of CO, there's going to be 2 moles of H2. And in 1 mole of H2 weighs 2 grams. So that's going to be 4 times 40 divided by 28 for a total of 5.7 grams. Well, I just told you that, right? Remember, this is what is used. Must know what's left over. Well, 5.7 minus 10 is what? 4.3? Okay. So that means you're going to have 4.3 grams of this stuff left over. So if you were in a chemical setting, there would somehow be 4.3 grams left over, and that's called an unreacted starting material. All right. 0, 4.3, 45.7. Okay. And maybe just very quickly here, if I could, let me write over here on the board to kind of put it in a method that you'll see 2 chemistries from now if you take it. Here's what we got. CO plus H2 yields CH3OH. So here's what I want to know. I want to know what is happening before the reaction even starts. That means you mix these 2 things together and stop the hands of time, period. Don't allow nothing else to happen. All right. You would start out with 40 grams of this. You would have 10 grams of this, and how much of this would you have? Nothing, right? We stopped the clock. That is before the reaction. Then we're going to let the reaction run. Okay? And all of a sudden, this is going to be after the reaction. All right, how much of this will be here? Nothing, completely used up. How much of this will be here? 4.3 grams. How much of this will be here? All right, 45.7 grams. Are you with me? Okay. So if you did an analysis when you're done, you would have a mixture of methanol and hydrogen. How do you get rid of the hydrogen? Well, maybe you want to suck it out some way. Or maybe you want to add just a little bit of CO and finish the reaction. All right. Whatever you want to do. Are you ready to go home? Let's go home then. That's chapter 9. All the problems, right?